Hi, this is Miss Fitzmaurice. This video is about when tau, or your net torque, is not equal to 0. So by the end of this video, you should be able to explain what rotational inertia and angular acceleration are. You should be able to relate this equation, sigma tau equals I alpha, and I'll explain what those variables mean, to sigma f equals ma, and you should compare the different I, and I in this case is your inertia of different objects. Alright, so far we've just been taking into account situations where all the torque is equal to 0. So let's say we had our meter stick from our meter stick lab, and we have a certain amount of torque from the meter stick from mg, and a certain amount of torque from like a mass hanging off of the meter stick, and we add both of those and we get 0. So we're in what's called rotational equilibrium. Okay, imagine instead that we have a disc, and this disc is like attached to something so it can kind of turn around. I don't know if you've been to a restaurant that has kind of a turntable in the middle so you can share food with different people. And we're applying a force to the side. So our net torque, if I add up all my torque, I only have this one force, and so all of my torque is just F times R times sine 90, which is equal to FR. And so I have this net torque, or this total torque, that's not equal to 0. Okay, so the question is, what is going to happen to this object? So you might say, okay, well, the turntable is going to start to move. And that's true, the turntable is going to start to move, and in addition, it's going to start to move and then move faster and faster and faster. And so what we have is we have this thing called angular acceleration. Okay, and it's almost the same idea as acceleration in a straight line, but instead of being distance, how your distance per time is changing, it's really kind of like a change in your angular frequency. And if you kind of remember, we talked about that a little bit during simple harmonic motion. Okay, so angular acceleration is the change in your angular frequency per unit time, or you can just think of it as angular acceleration is the rate of change of radians per second squared. So instead of acceleration being meters per second squared, it's how fast your radians are speeding up. Okay, and this is radians in the same sense of, 2 pi radians all the way around a circle, but it's how fast your radians are speeding up. So angular acceleration is this letter that looks kind of like an alpha. And we'll learn more about it when I do rotational kinematics, but for right now, I just want you to know it's how fast our rotation is speeding up, and it's in radians per second squared. Okay, so this sounds a lot like the fact that the total force is proportional to A, so I'm going to say it's proportional to my acceleration. Likewise, the net torque is proportional to angular acceleration. So the more torque you have, the more angular acceleration. Okay, and we all know that force is equal to ma, or that your acceleration is your total force divided by the mass. So it's kind of like mass slows the rate of acceleration down. There's an angular equivalent to mass, which is not quite the same thing, but the angular acceleration doesn't just depend on how much torque you apply to an object, but also it depends on this thing called the object's moment of inertia. And I'm going to give you an example just to sort of show you what moment of inertia means. So hopefully by now you have taken the time. I have had these two Jedi Knight sticks kind of hanging out in my classroom. And the main purpose of them hanging out in my classroom for the last couple of weeks was so you could try them, so I could use this video to explain what was happening. Okay, and these two sticks, one is red and one is blue, and both of them, they have the same mass. But the main difference, besides the fact that one is blue and one is red, is where the mass is located within the stick. So if you've picked them up, you will have realized that in the blue stick, each of them has two little weights, and in the blue stick, the two weights are kind of located at the ends far away from the center, but the red stick, there are these two weights, and they're located, and again, the weights have the same mass. They're located almost exactly in the center. And if you were to, I'm going to draw an orange circle to represent someone's hand. Okay, if you were to take your hand and put your hand right there and try to twist either one of these, you would find it is more difficult to twist the blue one, and it's less difficult to twist the red one. Okay, so the question is, why is that the case? Okay, and actually you might be saying, well, the red one and the blue one, they have a different torque, but actually you're twisting them around the same point. So let's say you're using the same torque, you get more angular acceleration for red than the blue. Okay, and it does have to do with how far away the objects are. If you are moving this blue object, you're actually, I'm drawing a dotted line, you're moving this thing, or you're moving the weights. If you moved it in a complete semicircle, you're moving the weights all the way along this dotted line. But if you twist the red one, you're moving them along this dotted line, so you're actually doing less work if you move the red one. One way to think about it is that the blue has more rotational inertia. And the red has less. Okay, so without giving you a formula, I'm going to do that in a little bit, but basically the definition of moment of inertia is how difficult it is to cause angular acceleration of an object. Okay, that's kind of like the fact that mass can be thought of, or inertial mass can be thought of, how difficult or how much resistance an object puts up to being accelerated. Okay, so this is kind of the relationship between force, acceleration, mass versus torque, which is kind of like the angular force, angular acceleration, and moment of inertia is the angular version of mass. Alright, so now we're going to talk about how to compare if you had two different shapes, how to think about comparing their moments of inertia. And the answer is that the moment of inertia actually depends on the axis of rotation. So first I have to explain to you what the axis of rotation is. And to show you that, I've drawn three more little lightsaber things, but let's say that instead of having two weights, it only has one weight, okay, and that one weight is located all the way at the end. So I have, this is just the same thing drawn 3 times, okay. The axis of rotation is the axis around which you rotate an object. Okay, so the way I'm going to draw it here, so if I drew an axis of rotation that went straight down the stick, then I would actually be turning the stick around in a circle this way. Okay, so where the weight was wouldn't really move, it's just kind of rotating in a circle around this line. On the other hand, I could make this dotted line the axis of rotation. Okay, and then I would be rotating up towards that axis, or sort of into the page and around. It's kind of hard to see. I could make this my axis of rotation, and I would be rotating again into the page and making this kind of rotate around this line. Okay, and you can imagine if you picked up this stick and did these 3 different things, it would feel a lot different. It would be probably easiest to rotate right here. Okay, it would probably be hardest to rotate in the second situation because your weight is moving the furthest. Remember, the plastic is a lot lighter, And then it would probably be somewhere in between to do this for third version. So what we can kind of conclude from this is that okay, so our moment of inertia depends on how far the weight or the mass is from our axis of rotation. And more specifically, I'm going to give you a formula for point masses. Alright, so let's say that we're holding this stick, and let's say the stick part has almost no mass, but at the end of the stick we have a block or a ball with mass m. Okay, if we're holding the stick and we're rotating it this way, okay, so we're rotating it like into the page, then the moment of inertia is equal to mr squared. And if instead we had a stick with two different ends and two balls, and I was rotating them again in the same direction, and the distance of each was a distance r, and each had a mass of m, then our inertia would be just the same thing as adding them up. I'd have mr squared plus mr squared equals 2 mr squared. And this is kind of nice if we have a bunch of point particles. But the question is, what if we had instead a shape? Okay, so what if we had a disk, okay, and this kind of brings us back to the beginning, and this disk is rotating around its middle, and it has a mass of m. We can't just use, and I'm just going to write I is not equal to mr squared, because while some of the molecules are a distance r from the center, some of them are only r/2 away from the center, and some of them are right at the center. So each molecule that had a mass is not going to have the same amount of rotational inertia. And although this equation is always true for individual little point particles or individual atoms, over the years, physicists have kind of developed a way to approximate what the rotational inertia is going to be for more complicated shapes. So what I'm going to give you is a bunch of different rotational inertias for the most common shapes. Okay, and this list is also on page 208 of G and Coley. But the main ones that I'm going to want you to know are a thin loop, and I'm actually going to redraw that. So the axis of rotation I'm going to represent with a dotted line is through the center. Then the loop will have I equals mr squared. Okay, for a cylinder, that we're rotating around its middle, so it would be spinning in this direction, then I is going to be equal to 1/2 mr squared. And this is supposed to be a cylinder. The same is going to be true for a disk. I equals 1/2 mr squared. For a solid sphere, I is going to be 2/5 mr squared. And then finally, for a rectangular, or I guess a cylindrical rod that you're rotating around its center, I equals 1/12 ml squared. Alright, so the last bit of information that I'm going to give you today regarding moments of inertia is what's called the parallel axis theorem. So we know from the last chart that if we have a cylinder and we're rotating the cylinder around its middle, that the equation for I is equal to I equals 1/2 mr squared, and we'd be rotating the whole cylinder around its middle. Okay, but what I told you is that the rotation, or the moment of inertia, or rotational inertia, you can use those two interchangeably, depends on the axis that you're rotating it. So what if, instead of rotating it around its middle, you were to take a cylinder and rotate it, the whole thing, so this is the whole cylinder, around its side? Okay, and the answer is that you could calculate, and I shouldn't have drawn that last center line in. I'm just trying to show where the center is, and we have a distance r. To calculate the new rotational inertia, or the new moment of inertia, we use the old one, so I'm going to call this IB is going to be equal to our original one, IA, plus 1/2 md squared, where d is the distance the axis of rotation has been moved. Okay, so for example, in this situation, we have IB is equal to IA, which was 1/2 mr squared, and then we've moved it a distance r. We've moved the axis of rotation, which I'm highlighting in green, a distance of r out to the side, so we have to add plus 1/2 mr squared, and the new axis of rotation, or the new moment of inertia, is going to be 1/2 mr squared plus mr squared is just mr squared. And this is true in general for any shape, and let's say the shape doesn't have to be a regular shape, it could just be a blob. If we knew I of our blob, okay, and that's its moment of inertia around this axis, if we decided to move the axis we were rotating it around. A distance d, then the new moment of inertia, let's call it IB, in general, IB is going to be equal to IA plus 1/2 md squared, the distance we have moved the rotational axis. Alright, so I know that this whole thing is probably a little bit complicated and possibly a little bit confusing. What I want you guys to do for tomorrow is I want you to come with questions about this topic. And we're going to spend a little bit of time in class addressing those questions. So make sure you do that for tomorrow. I'm also going to put out a very short video on rotational kinematics, which I would also like you to have questions for tomorrow. Alright, see you guys tomorrow.